So we're gonna do a little Q&A just for a little bit, and then what we're going to do is we have a in-person guest that's gonna come in on the stream in a minute, and they are going to be talking about some of their research in theoretical quantum physics. Yeah, we got a theorist in here. So when the theorist gets here, we all have to make fun of him because he's a theorist, and I'm an experimentalist. That's kind of how we have to go about things here. So yeah, that's gonna be really cool. We're gonna talk to a theorist on his research in theoretical physics, kind of like what's that life about. We're also gonna talk about like how did they get into research? How did you figure out this is something you want to do? How can you build yourself from a point of I barely know Calc 1 to I'm doing research at an extremely high level and I somehow understand some kind of math now. That's kind of what we're going for this discussion. It's gonna be cool. And instead of last time where it was someone over a call, they're gonna be sitting. Probably get a chair. That's a bad host of me, isn't it? That's a pretty bad host. I'm gonna be like, yeah, just sit on my bed. You're just gonna sit right there. I'm gonna have to like move the mic so it picks up both of us. Yeah, it's a very jank setup. I don't got that professional. I don't got two Shure mics right here where both people can talk into them. Get it? Yeah, we'll get a chair when they get here, I guess. Just come in. Open the door.
I don't know why I didn't think about the fact that I.
Oh, you brought a chair. You brought a chair.
I'm well prepared.
Nice.
Oh, it's so nice in your room, Dario.
It is nice and cool having AC. Everybody, he is here. This is, so can we talk about, the last time, for anyone who's here last time when Kershs was here, this is Kershs also, this is Kershs. The last time he was here, he was trying to get me to end the stream because he wanted to go watch.
We were already like 20 minutes late, by the way.
And I was like, yeah, I'll end the stream right now. And then I just kept asking questions.
To be a pretty bad hockey game, to be honest.
Yeah, but let's talk about you.
Oh, okay.
Less about me.
Okay.
Because I talk about myself enough.
Oh,
so
I know.
I know who you are. I know who you are.
Really, what's my name?
Chris.
Oh,
C-H-R-I-S.
yeah. No, it's actually Christopher.
Yeah. Christopher.
Yeah.
Yeah. But so feel free for people who weren't here last time. Oh wait, yeah, we gotta take the thumbnail. Thank you, Arnav.
Oh my god.
We gotta do the thumbnail, and then we're gonna get right into this. We're gonna get right into it. Wait, I gotta turn the chat off for a second. Okay, we gotta pose.
What is this face you're doing, man? Are you constipated?
You're the one that's doing that.
You're doing the. Okay, it's
all right, and then Arnav should have done something with that and sent it, and then dude, did you take it? I don't know if he took it. Do it again. Oh, wait, where do you say do it again?
Right here.
Oh. Did you take it? I gotta imagine you got it. I have to imagine you got it. Did you get it?
I'm staring at Discord next.
Oh my god.
Oh my god.
How hard is it? Okay, we'll try again. Wait, maybe we should evenly space ourselves a little bit. Okay. No, I didn't mean get. Okay, whatever. This is fine. Hold it! You're blinking!
Am I supposed to make a stupid face?
I don't care what you do.
Damn.
We got it.
Okay, there we go. What is research in theoretical physics like? Oh, okay, so that's actually a good
Wait, we're gonna get to that. That's gonna be what we're talking about. We're gonna talk about that.
To be you, I guess.
That's what we're talking about. That's the point. We're gonna talk about what it's like. Boom. All right, let's get into it. So now that their thumbnail catastrophe is done, Kershs, feel free to introduce yourself. Talk about so what kind of research do you do? Give it like a layman's term overview.
Sure. So I've been doing kind of theory research, I guess, for a little bit now. I started in undergrad, and right now what I work on. So me and Dario are both in the AMO field of physics.
Atomic, molecular, and optical.
Yeah, we can kind of outline the fields of physics in a little bit, but so it deals with a lot of cold atoms, specific quantum effects with atoms or whatever. So what I work on is, your GPS, right? You have a GPS or whatever. A lot of GPS is used interferometry, where they use light basically to figure out some really precise signal of how far you are, where you are, this kind of thing. Right. Well, what I work on
Could you describe very briefly how a GPS, like a conventional GPS,
sure.
How does that work?
Yeah. Oh, that's.
I can answer that.
No, but that's like a
super simple. How do we get how does your phone have your location?
Yeah. So what usually happens is that effectively you can think of it very simply. It's like you exist on the Earth, right? There's a bunch of satellites in space. That satellite is shooting light beams to you. Let's say one satellite is at their equator, one's at the North Pole, right? The amount of distance those light beams travel is different between the two. So they'll shoot a light at you, get the feedback back, and they'll be like, oh hey, it's this far apart. Therefore, we can kind of make some inference of where you are on Earth.
And they use a few different satellites to ping a location.
And also, for the record, super cool. For all that kind of stuff, you need relativity. You need all this stuff. So people don't appreciate that, right? What is the practical use for relativity besides cosmology? GPS. You can't have GPS without special relativity, which is pretty cool. So what I work on though is that's all light kind of stuff. I'm trying to do that with atoms, and the benefit is that a lot of quantum or atom things, it's a lot more precise. So we can do gravitational wave finding. We can do stuff like having really precise GPSs. Another big application is that you could use it for space travel. So right now, I told you, right? You're on Earth and you're trying to use a GPS. You need some reference frame, right? You need these satellites floating around. But what if you have no reference frame and you're just like in the deep nothingness of space?
So we're saying now we're taking this thing, we want to put this on a spaceship.
Exactly.
Okay.
Yeah. But there's a lot of applications, basically. You know, as things get more and more precise, you can open up more and more uses for them. But basically, in summary, yeah, that's what I do. I try to basically make atom interferometers, design them, and that kind of thing, among other stuff, or atom devices, I should say, that hopefully in like a few decades we can start using them on Earth. You know.
So in the simplest terms, from my understanding, normal GPS is like I'm on ground, satellites are in space, I'm pinging between them constantly,
Sure.
and I'm using feedback from those signals to understand where my location is.
Sure.
But I'm a reference frame because I'm on Earth and they're in space and we know where they are.
Yeah. Honestly, the analogy kind of breaks down because I mean, like, you can have optical interferometers that don't need a reference frame.
Yeah.
Right. My whole point is that basically right now, for all these really precise devices, we use light, and using atoms can like make it even more precise. And that's kind of what I'm working on, just atom device in general. I worked on lasers, for example, undergraduate. Dario worked on just junctions. So it's a very similar concept, right? In that case, you know, you have lasers and they use, for example, in my case, they use regular light. And I was like, what if we put some spin, which is this quantum property in them,
Yeah.
make them better?
So you're trying to make a more sensitive kind of quantum GPS in a way.
Sure,
You
we
can make
call
it.
it
We can
quantum GPS.
we can dumb it down. We can call it a quantum.
We'll call it a quantum GPS.
But then the technical word would be like an
Hell yeah.
atom interferometer.
Yeah.
I saw the university put out a story on your lab very
Yeah,
recently.
that's true.
I did.
Our
I
lab
did
is
see
pretty
that.
cool. So what's also cool about my group, for the record, is that we have both an experimental and a theoretical kind of like side of it.
That was my next question. I was
Oh.
gonna say, Chris, this sounds a lot like some experiments are going on. You said you're a theorist. What's
You're damn
going
right.
on here?
You're damn right. What's cool about my lab, for the record, is that we also have a lab itself. So this atom interferometer I'm talking about, we're testing it ourselves in the lab, which is super cool. So for example, right now I'm trying to work on is, like, you know, we have this atom interferometer, right? It uses neutral atoms. So right now it can sense like gravity and whatnot. Okay? I'm like, hey, what if we can sense magnetic fields? So we may make a magnometer. So what I'm trying to work on right now is developing a magnometer that they can then hopefully just take my idea and just test in the lab.
So you're working on the theory, and then you have the benefit where you have people in your lab that are experimentalists,
Yep.
and they can immediately be like, "That's cool. Let's go
Yeah.
try that."
Yeah.
So I guess here's a good question: what would you say is the main difference between doing these things experimentally versus theoretically? Like, what are like they go hand in hand, but what are you doing compared to what the experimentalists are doing?
That's a good question. Like it's kind of like, let's say you're trying to get to a destination, right? I'm the guy drawing the map, and they're the guy making the trail.
That's
That
a
kind of
good
makes
way to
sense,
put it.
right? So like, you need to know the route, right? You can't just go to the top of a 14er or whatever and just try to send it. You
Yeah.
need to know roughly the route, but there are still a lot of practical things and a lot of like non-trivial, super hard things of making a trail. You know, you gotta make sure the angle's right so it doesn't like run off water, doesn't like mess up the slope or whatever. A lot of things. And I think that's how I would put it. So in practical terms, I'm making kind of like the algorithm, or like, you know, the procedure we want to do. How do we want to mess with these atoms? What's actually the best way of getting this precision or whatever? And they're gonna actually implement it by like figuring out, hey, how do I actually get this magnetic field to work at this level, whatever, this kind of stuff.
Yeah. What would you say? Another good question on there. What would you say your day to day is like?
My day-to-day is pretty flexible, so this is one of the bigger reasons I chose theory.
Yeah.
But like my day-to-day basically is I go into the office like 9ish. I just do work at my desk or whatever for so long. Yeah, I'm in a room with my other group mates or whatever, so I can chat. There's a whiteboard there. It's a very chill thing. It's also theory, so I don't like log hours or anything. You know, like it doesn't matter if I work for 8 hours staring at a piece of paper or read it in an hour. You know, what matters is that I get work done. So that's my day-to-day. I will say I like going to the office specifically because for me, it's really easy to work on theory at home. And you kind of don't want to, right? At some point, like, you don't want to always be locked in. It's kind of a lot. So I kind of like having the separation of like, oh, definitely work on research out here. And I can work on it at home, but I don't need to, kind of thing.
Yeah. Because for you, like what I see from you is like if you wanted to, you could most of the time never walk in lab.
Oh, of course, yeah.
And you could just be at home.
Yeah,
I
I
have days where I can go home,
Yeah.
but I have many days where I'm like, I have to physically be in my
Yeah.
lab.
The only reason I would ever have to actually go in would be to meet with people, right?
Mhm.
Or for group meetings or whatever. And that's just because it's nice to have this in person. But yeah.
But no, I think that's a very good point to make. And someone said, like, what's stopping someone from being an experimentalist or a theorist
That's a good question.
in physics?
Yeah, so I think it's okay. It really depends, right? I think okay, also experimentalists still have to do theory. You know what I mean? There's this misconception, and I think really good experimentalists do theory, like properly, you know?
Yeah.
Like for example in my group, our experimentalist, she's freaking brilliant in my opinion. But she like works out Schrodinger's equations. She does theory, you know what I mean? It's just like it's nice to have people who are like full-time theory to work on more trickier questions of like I don't know, figuring out like atomic squeezing or some of these fancy things, right? So I think the line starts blurring. What I would say is it's really a case of like, okay, I think it's a thing of time and effort, really. If you have an experiment, you want to kind of just like, first of all, experiments are expensive.
True.
I should start with that, right? They're freaking expensive.
My basic equipment orders are like thousands.
$100,000 or so, at least, right, on an experiment. It's kind of hard for you to be like, okay, I did this one experiment on it that I was designing it for. I'm gonna go like mess off to the whiteboard. You're kind of like, I spent $100,000 on this. Let me like milk this thing for every possible scenario I can think of, right? And that's time. That's just time. And as a theorist, right? Like you're kind of constantly learning. You're getting very deep into these things. And that also takes time and effort, you know, and just thinking about these things. There's a question that says, Einstein once said, imagination is more important than knowledge. Do you have any suggestions on how to get more creative or unhesitating in terms of imagination? I would say, I agree with that for the record. You can only compute stuff for so long, right? So how to get more imaginative or whatever, I think what a lot of people do sometimes is they focus on like what they're specifically supposed to work on. Like if I'm a quantum computing physicist, right, I'll only read quantum computing stuff. But it turns out that science doesn't really care about our labels on science, right? A good example of this is that right now somebody in my group is working on quantum information, and our postdoc has a general relativity background, and he's managed to apply that general relativity background to quantum information. But this connection never would have been possible if, you know, we didn't have these different fields coinciding. So I guess my suggestion for better imagination would just be, don't focus on the exact task. Sometimes looking into other topics just has links, and that's I think that's how I view imagination. Is just, can you build intuition in different fields where you can start like pattern matching them together.
Yeah, I think that's a great way to put it. How do you get the ideas to draw? Oh, that's a good question. Draw them. Like, how do you get the ideas to draw that map?
Yeah, that's actually a very good question. Again, this is just a question of how do you build intuition, right? If you just kind of learn enough in the field and read enough papers and talk to enough people, you just start like making guesses, try to work out your guesses, and you're like, okay, was this reasonable or not? And that's kind of how it is. It's to a certain degree is trial and error, but it's trial and error guided by your intuition, which is really, your intuition is just guided by all the stuff you learned in the past. Oh, the tangent I want to go on though is I think it's really interesting. Theory experiments are really interesting to compare because, like, my experience as a theorist, right, is that I think there's a harder initial learning curve, but once you get to the point where you're past the curve, it's a lot easier to like get output out. Like, what do I mean by that? I mean, like, usually as a theorist, you spend like the first year or so just reading papers, like pretty much reading papers. You know what I mean? Just
I've seen some of your papers. Stuff, I believe that.
And it's just hard stuff. And like, for example, to learn atoms from you had to learn like Bayesian statistics and like all this other stuff. But then once you actually get to that intuition, develop that intuition, it's really easy at a certain point just to pick problems and just go with them. Versus experiment, you could point Dario to a lab and be like, hey, look at that device over there. Go fiddle, you know?
Yeah, I can,
and there's
I can fiddle.
There's quicker feedback on that, right? But once that project is over, you have to kind of like start scratch for a new experiment, right? So there's kind of like bigger turnover.
Yeah, wait, this is probably a great time. Can you tell me one of your papers?
One of my papers,
or not? Sorry, papers? One of your lab's papers. Show me one of your lab's papers.
What do you want right now? Like, what are you savoring?
Give me something scary. Give me something scary.
You want something scary?
Give me something. Give me something. I want it to be something that you understand. But when
okay.
someone looks at it, they're gonna be like, "What am I looking at?"
I have a good one then. I have a good one. So maybe let me give you a bit of context for this paper. So earlier somebody said, is physics stuck? And that was a great question. I'm glad somebody asked that question. So this is also a really good thing of what I meant of theory versus experiment. Okay, so my PI is this guy, right? MJ Holland. Let me give a bit of background. Okay, so you got lasers, right? And you want to make lasers super precise. Let's say that's our goal, right? And I'm not going to say what precise is right now. I'm just going to say super precise, okay? Turns out, right now, you can kind of think of lasers as you have two mirrors and you bounce photons in between. And the mirrors and how stable the mirrors are determines how precise the laser is.
Am I looking at this image here for that, or?
Sure. Yeah, actually, sure. Go up to that image. So, you know, let's say you have... That's actually not what that image means, but we can pretend that's what it means.
Is there a better one?
I don't think so. This is a...
Could we look up a better one? All right,
so,
there you go.
A really simple example. You got two mirrors, right? And usually you can think of photons as bouncing between. And, you know, how precise the laser is how stable these mirrors are. There's this really cool idea.
What does precise of the laser mean?
Okay,
like, very briefly.
Yeah. I didn't really want to get... Okay.
No, it's just super brief.
Precise by laser, I mean that, like, a laser is supposed to be one frequency of light. By precise, I mean how much of the laser is that one frequency of light as opposed to, like, being, like, 1% off that frequency of light. The whole revolutionary idea, right, which some guy named, actually Robert Dickey, had, which is funny name, guy from Princeton. We can exploit this thing called collective motion, and I'm not going to talk too much about that.
I assume not.
Yeah, but basically, we can actually instead kind of shake the mirror, or have the mirrors not be super stable, but kind of like mess with the photons to make the thing stable. It's basically just like flipping the laser concept to get a really precise laser, but it's like a whole new idea of how you do it.
So instead of stabilizing this laser by making the mirrors super perfect distance from each other,
Exactly.
we're now intentionally creating some noise.
Yeah, and we're messing with the photons instead in the middle.
And yeah, okay, now the photons are going to
Before
be
we cared about is the mirrors, now we care about it is the kind of atoms with the photon.
Now back to the paper. So this paper
and making a precise laser.
is Murray kind of being like, hey, I had this idea for this laser.
and he was like, this is how the map looks like. It's this image right here, basically.
So this is our map.
This is our map.
Our visual map.
This figure 1 right here.
Okay.
And hey, if you do this, it turns out we can get. So, before we're talking about precision or noise, right? Precision. Yeah. And let's say before is at 1, right? Just 1, value 1. We're not
Precision of 1?
Yeah.
Okay.
He basically saying, hey, I could figure out this concept of a laser. Oh, we can get it for precision of like 1,000.
So we can make it 1,000 times better.
Exactly. By just
doing
having this map of a laser.
Okay, and obviously, and now to get back to make sure, I'm sure people are looking at this and are like, what are we talking about? What are we looking at here? The question was, how do you come up with this kind of map for how you're gonna make things? And a lot of it is kind of these visuals and analogies in the end, and it's kind of like the math builds a picture in your head, would you say? And you can kind of use the physics to
make a map? It's like you kind of like, so, for this laser, right? You have this idea of, hey, what if we keep the mirrors kind of shaky and make the atoms really precise, right? And then what Murray basically just did is that he knows all this extra other physics, right? And he was like, okay, how do I fill in the gaps between the shaky mirror to make it into a laser? And then how do I mess with that so it's really a really good laser? So it's almost like knowing a bunch of pieces and connecting the dots.
Okay,
and
so
connecting the dots is the intuition part. That's the imagination part. Is how do you connect the dots effectively?
So he has enough intuition that he went, I know about this thing, I know about this thing, and I know about this thing.
Yeah.
I have enough knowledge of how this works that I'm going to find a way to connect these different things together and create the new thing.
Yeah. And that's what great physicists do, right? I think Feynman was a good example of that. Feynman did particle physics, and then he was like, I just know enough about physics for I'll start doing, like, super fluid physics.
Yeah.
And he was great at it. But that's not his field, right? But he could take the intuition and the random ideas he knew. Like, he famously talks about when Feynman was building the atomic bomb. He's like, I had this, like, random calculus, like, tricks book from, like, high school. And it was really useful, actually. And that's what I really want to get at. I think people have this misconception that you're supposed to, like, just, like, grind your field. No, if you want to do really good science, I think you actually should kind of try to be broad, in my opinion, to a certain extent.
Yeah.
Right? And, like, you never know. It might not be useful for, say even a decade, but maybe you'll come across a problem where it's like, damn, that's a sick shortcut, and nobody else can see that in the world.
And people are probably looking here and looking at a lot of math that I don't understand. I only
what's funny?
I
This
understand
is
the
one
notation.
of the most mathy paper stuff.
Yeah, those. I've seen some of your other ones.
Yeah.
Now I understand all the notation here, but I obviously don't understand what's going on. So it's like this would be gibberish to most people, and most people would get thrown something like this, and they would be like, "Whoa, I could literally never do this."
If your PI throws you this paper off the bat, like as an undergrad without taking
no, but like, I just mean like people get exposure to these things, like, especially when they first start out, and they just see these things existing. Because sometimes your PI will give you like a folder of papers and be like, you're gonna read this one, but here's the other ones that encompass this work. Like, how do you not be overwhelmed, and how do you like get to a point? Because I mean, I'm seeing people be like, I don't get this at all.
Yeah,
I stick to law guys. That's
I've only
okay.
looked at this math like once, right?
Yeah.
And even I don't focus on it too much. I think the biggest thing is if you can pretend like you're explaining a paper to somebody, that's one of the most helpful things.
Mm-hmm.
Just like pretend like you saw this paper, right? And you're just reading like the abstract or whatever, and you're just trying to figure out, hey, what can I confidently say to somebody else where I'm not lying and it's something about this paper.
What I actually like doing, for the record, is I just kind of like
read through stuff, and if I don't know a word, I'll just search it up. Especially in physics, I think we have this a lot, where it's like some random guy's name in terms of like a theory or a theory.
They're like using
like like
Timothy Chalamet's quantum field theory concept.
So
like,
what I'll literally do is I'll like in my notes, right? I'll just do a thing called a side. I'll make an open parentheses.
Yeah.
And I'll just search up that theory, and I'll just be like, okay, let me read through this entire theory.
Yeah. So it's kind of like so a lot of times to approach something like this, you're doing like very like it's a slow process, especially in the beginning, where every time you're hitting a new word, you're like, okay, I don't know what ultra narrow clock transition is, and now I'm gonna go look up what that means. I'll be on a tangent for like 10 minutes, figure out what that means, and when I come back to it, I'm like, I understand that now. I think for anyone who aspires to not just do high level like physics research, because this isn't initially I want to do a lot of conversations with people I know and they're going to be in physics, we're eventually going to talk to people who aren't just purely in physics, and we're going to have conversations with them about what they do. And in the end, all of their papers, the similar thing, every single one of their papers are going to look confusing. And they're going to look like you're like, I could never do something like that. And I get math is the most in your face kind of, how could I ever do that? But in the end, if you do stick through these things and you keep working at them, eventually these things make sense. I mean, a lot of you probably learned integrals recently that are in the chat, and you probably would have looked at yourself a few years ago and been like, how do people solve something like that? But you figure, like, you just keep going, and you figure it out. Like, this stuff, if you get to the point of being able to understand it, it's not too bad. I feel like it's a good discussion to have. How did you get into doing research in the first place?
Effectively, end of my 11th grade, I was like, okay, I gotta, like, test this theory that I want to do physics research. And I'm like, okay, how does one
You
test
said 11th grade, clarify.
End of 11th grade, yeah.
So you just finished your 11th grade year of high school.
Yeah, exactly.
Okay.
And I was like, okay, how does one test the theory of, do I like physics research? And I'm like, okay, well, I should do physics research. So we're very fortunate to live close to University of Buffalo, which is an R1 school. It's a nice school, go Bulls. But yeah, so I kind of like looked at the physics website. Yeah. So basically, I knew there was a pathway, or like it existed, that people as high schoolers would like do something at a college.
Yeah.
So I looked through the physics website at University of Buffalo, and I was like, oh, these people look cool. I think I picked a professor because he had lasers in there, and I was like, man, I like lasers. Lasers are cool.
Wait, can we make that clear real quick? You just said that that's a big point to make. You just said you just finished your junior year of high school.
Yeah.
And then you just went, I feel like learning more about if I want to do physics, so I'm going to go look at this university's website, and I'm just going to email a professor.
Yeah, basically. Yeah, pretty much.
And you can do that.
Yeah. Well, also, it's not even like I was expecting to get anything out of it, right? I was like, at the very least, if I can just talk to these people and just like be a bum, around them for a little bit, I can like kind of gain a little bit of what it's actually like, right? Yeah, so I reached out. This one guy was like, sure, let's try it out. But like, through my senior year, for the record, I didn't do any productive research my senior year. I was given like this thing called like spin laser papers or whatever, and I got so mind messed up by in like a good way, right? Of like, I'm like reading through it and I'm like, what do these words mean, man? Because it was like, a proper research paper, right? Yeah. And I remember the only task they gave me was like recreate this one really simple figure, and it was really just taking an equation and solving it and putting it in Mathematica.
Wait, let's make sure we clarify the steps here. You reach out to the professor.
Oh yeah. Let me go slow. I reached out to the professor. I met with him, and he was like, yeah, I'll try this out. I'll waste a bit of time with you.
I think the point to make there is that you just blindly reached out to a professor at a university as a high schooler.
Yeah.
And they went, sure, come meet with me.
Yeah, exactly.
I think that's very important I don't think a lot of people understand that.
The first meeting, for the record, was like, hey, how serious are you? Are you some guy who like watched PBS Cosmos and it's like, I want to solve the black hole mystery, And I was like, no, I just kind of want to like try this stuff out. But yeah, so that's true. It was literally just that. And then I said my meeting, I met with him, and the professor was nice enough to be like, I'll waste my time with you two, right? Obviously. In a good way, in terms of like, because there's no guarantee, right? He's just doing it for community development and for physics development or whatever. So he gave us a really simple problem, which is read these papers, plot this thing, which is like basically lasing power to lasing output, okay?
People don't know what that means, but he's making a graph.
That's
fine.
Making
a graph.
You're solving these equations basically, and making a graph, right? But these equations are like part equations, they're partial differential equations. Yeah. And I didn't know Mathematica, which is the code he wanted me to use. So for like basically a year, on and off throughout my senior year of high school, where I'm obviously busy with other stuff. I'm not putting as like insane amount of effort into this, right? Eventually, and then I stuck with it. I actually got paid going into my freshman year because the guy was like,
college.
Damn. College, yes. Yeah, college year.
So you decided to go to the university then and continue.
At University of Buffalo, exactly, because it was COVID, and I was like, I don't know if I want to go to a city right now. But yeah, the guy was impressed that I stuck with it, got paid that summer, kept doing it 4 years, got 2 papers out of it, pretty good time.
So I think it's an important point to make to anyone here. If there's anyone here who's in high school, it's like you very much can reach out to a professor and show genuine interest.
Yeah, I will say, I'll say a caveat here. 2 things, okay? One, it's easier for professors to kind of entertain you, I should say, as theory. And that's both a good and a bad thing. I did spend a year just trying to get like the basic understanding of being useful, just solving stuff in Mathematica and plotting it and like messing with numericals.
But even just putting in that effort,
I know,
meant a lot.
But that's one caveat, right? It's easier for theoretical professors. Versus experimentalists, you would have to show up, right? Theoretically, and like actually like turn knobs, and that's kind of like a hard thing for people to do sometimes. Is like let this like below 17-year-old turn knobs in your $100,000 experiment or whatever.
True.
Right. So I will say that's a caveat. So, but yeah, if you're persistent and you want to get something going, at the very least, people will definitely I think are prone to entertain you in terms of like giving you papers to read and being like, hey, let's just set up meetings and talk about this and see how if you show commitment for a few months, you can get involved or something.
Yeah, and doing even just that in high school, even though you like probably didn't even know what you're doing, like that in depth, it put you on a very good track of understanding kind of what the field was about, and it gave you. And then as you continue undergrad,
I think more than anything too, it just made me sure that I wanted to do this.
Yeah, and it got you scholarships, and it got you a lot of it got you papers eventually as you kept going, and eventually gets you into good grad school.
I will say one caveat though for the scholarship thing.
Yeah.
And this is, I think, back to my point of like you shouldn't just turbo focus, because I feel like a lot of people in STEM do this a lot. And they're like, see these good degrees, just read do the stuff and it's whatever, right? I think there is some value to being well-rounded as like a person, right? Like I got the scholarship for the record, so I had to get interviewed. It was like a full ride scholarship at UB. Yeah. Right. And they didn't have any physics professors because the physics department is kind of small. So they gave me a history professor because I liked history as well. So I just talked about the Gilded Age the entire time.
Oh, really?
And then the guy asked me like what my favorite episode of The Office was, and this random ass stuff. Like I didn't actually demonstrate the recommendations probably helped from the physics stuff I was doing. But the interview was the final barrier, and I got that because I was a well-rounded person and I like talking to people. But I think there's something to be said about I think we have a misconception in physics or in STEM that stuff like reading and writing and talking don't matter as much.
Yeah. They absolutely matter. Having communication skills in science matter.
Being a good writer, being a good talker has helped me a noticeable amount, I would say.
Yeah. How long does it take to develop a working model or simulations? It basically saying how long does it take you to develop one of these papers?
This is where I'm kind of getting at with the learning curve thing, right?
Yeah.
Higher learning curve, where I think, give me those maybe 6 months and I'll finally get proper intuition, I'd say. And I'm just ending my first year right now. Right? Yeah. But once I'm up there, for example, some of the senior grad students in my group, right? Yeah. They could probably come up with an idea for a paper in a few hours, because they just have that level of intuition.
And then fleshing out
over a month or two.
Okay. Right. So yeah, I think that's probably a good way to put it. Is if you're new in a field of theory, then it could take. It takes a while to get 2 years even. Yeah. To be able to get something and a good enough foundation where you can do something with it. But then once you get that foundation, now you're talking about the students that are getting ready to graduate.
Yeah, and by foundation I mean intuition, right? Yeah. Intuition to come with new ideas and imagination or whatever. Yeah. Right, because that's not just learning stuff. That's learning stuff at a deep enough level where you can make guesses and fill in the blanks.
Yeah. So that's kind of a probably good way to put it. And then also, then you look at the senior students in your lab, and they have so much intuition in that field. And they have such a good foundation.
Or even your professor, right?
Yeah.
My professor Murray.
And they're pumping out ideas.
Oh yeah.
In a couple months.
Some of my people in my group have just a document with just ideas, which they think would all lead to papers.
So they have more ideas than they don't have time.
Oh, 110%. Yeah.
And it's a good thing to point out.
Yeah. Versus an experiment, right? You could argue that sure in the first year you can maybe get a paper out, right, or whatever. It's there, right? It's there. It's physical. But what if you're trying to make a whole new experiment, right? That's a decent amount of kind of turnover right there.
Yeah, that takes a lot to think through.
And that's why, personally, for the record, I chose theory. Is I like having the freedom of working on multiple things at once and what I want at the time. Versus if you invest $100,000 in an experiment, sucks to suck if you don't like it, man. You're just doing that for a year, I would say, right? You gotta spend the money.
Yeah, I mean, usually it's once you're committed to experiment, it's don't.
You gotta see it through.
I'm doing something right now where I'm getting parts together.
I could stop a project and just start a new project.
Yeah. See, I can't do that. Yeah. It's very much I'm committed to being this idea. I'm putting thousands of dollars.
No, I could go to Murray and be I don't like this idea, Murray. This is boring. Give me something else, kind of thing. Yeah.
Murray, your PI, just so people are clear.
Sorry. Yeah.
Would you say a PhD in engineering basically teaches you how to solve any problem in that niche? No, definitely not. I mean, I feel like the very simple answer is no.
If you're doing an experiment in frequency combs right now, you could not do experiments just by default on atom interferometry.
Yeah, even though we're in the same.
For example, you don't work on any cold atom stuff.
Yeah, I am in the same field as Krish. Now, Krish is an experiment. Let's say talking about the experimentals in his lab.
Yeah, exactly.
We're in the same field, but we do different things. I can't walk in there
and be useful instantly.
Yeah, I can't do that and immediately just know what's going on. It's very broad, and that's a big thing of what we're trying to do here. So we're trying to give you exposure.
And this is also to something problems out there. To be said, right? Science doesn't really care about labels. Yeah. At a certain point, if you're a physics materials researcher, right, you're kind of almost closer to an average physical chemistry PhD than you are to a high energy theorist. You know what I mean? Mm-hmm. It's all kind of links together at some point. So, no, you can't just get a PhD in electrical engineering and solve any electrical engineering problem.
What would you tell someone is a good sign that maybe they want to study physics?
I think for me personally, I like physics a lot because I just like solving problems. Mm-hmm. I remember in high school, they brought a charged rod near a faucet and the water bends, right? Mm-hmm. And I was like, that's freaking sick. Why does it do that? That's freaking sick. Mm-hmm. Versus there's also the people in physics who are like, they watch like the PBS Cosmos stuff or whatever, right? And they're like, I want to solve the black hole mystery. And I'm like,
Which, to be fair, people do work on.
people do work on, yes.
But I think the big misconception that people have is that they come in and they're like, within my first year of undergrad, I want to be working on that.
So let me put it this way, right? For example, I remember actually one of the people either a year below me or my year, when they're taking physics 1 and 2, they were like, okay, so when do we get to the real physics? And I think the big thing I would say, 2 ways to know, is that you could always just try looking through research. If you just like the idea solving questions where you don't have any path to, that's a good example of studying physics.
Yeah.
But also, unironically, if you take a first year physics class and you enjoy that, then you probably do want to stick with physics. What you should be wary of is you get like, okay, let's be clear, right? Most of the physics 1 and 2 classes are like those engineering ones, which is like, solve for this number, right?
Yeah, they can be kind of dumb.
Yeah, and they're kind of dumb. If you like working on just like physics problems, right, and building them up from first principles, that's a good thing. What I don't think people should think about is that, oh, I'll get to some year in physics, my 3rd or 4th year, and suddenly it'll be the cool physics. It does get cool, yes. But this idea of you build up a problem from its roots up, I think it's consistent. And I think if you enjoy that, that's a good example of you liking physics.
Yeah. And I think the big thing that scares a lot of people away from physics when they come into it is they come in being like, why am I not doing things on black holes and stuff immediately? Like, where's the physics that I want? And it's like, you're not going to get there for like 4 years minimum.
Yeah, like
and,
properly, right?
Yeah, properly.
And again, this is all like what you mean, right? Like you could theoretically like read, like, you know, run some code, right, on black holes.
Yeah.
And you could say you're doing black hole research.
Yeah.
You know, but like how much of the code you make yourself, you know, like how much you actually understand it, this kind of thing. Yeah, I agree. To do proper stuff in depth, I would say, you know, I didn't really, even in my undergraduate research, I don't think I properly understood stuff where I could like start thinking of my own problems until my senior year.
Yeah, that's fair.
Yeah.
I remember a big thing we're trying to do, this is to, like, to everyone here, a big thing we're trying to do here is talk about like the more human side of science. Sure. And like these are 2 people here doing research in like science on these things, like these weird problems.
That's true. People are saying this.
We're just dudes, you know? We're just dudes.
People are saying that,
Dudes who
go off.
Yeah, pop off. Like people who do science aren't like just all bots who
I would hope not.
No, they're like most of the
It'd be
time
really
they're not.
boring.
Especially
Actually, I will say there's something you said about like if you're doing a PhD in like a decent school in physics, people are usually pretty interesting.
I was like I was
because
really...
you have to just have some kind of discipline, right, to get there, and then you need hobbies and like personal management of yourself, right? But yeah, like for example, we have a friend Joe who is like really into physics, right? But me and Aaron, our another roommate, went on a hike with him, and he's like, yeah, like he goes on like random like winter backpacking hikes all the time and this kind of thing. He's like a really cool person, you know, even if he is incredibly smart in physics.
How do you maintain balance in your lives while putting a lot of effort into your research?
The way I balance it is, I mean, for me at least, in undergrad, it was really busy. Like I was doing work a lot of the time. I really don't want to pretend I had a work-life balance in undergrad. In grad school, I think I'm doing a lot better. And how do I balance my life is you kind of, I think it's a good way to keep a schedule of what is research life and what is life, and how do you make sure you dedicate some time to both of those. And I think it's easier to do that in grad school, but it's also about the environment you're in. It's important when you're finding labs to join. There's gonna be some labs that are like, I expect you to be here from 9 to 9 p.m. And for me, when I see that, I'm like, okay, that's not a lab I'm gonna join. Simple as that. I'm not gonna join that lab. I'm gonna find a lab that doesn't make me do that.
Yeah. So let me answer that. I did classes, and I skipped ahead a year in classes too, my junior year. So I did all my senior year classes my junior year. We had rocketry.
We made rockets.
And we had physics research, right? So it is correct in terms of time. Perhaps it was not balanced in the sense that like I would come home at like 9 and start doing homework. Probably isn't great, right? In terms of time, it was busy. How do I balance it? I think I've been pretty good about realizing that my career is a really long career, right? You could theoretically, you could do physics, right? Like I have professors I worked with who are in their 80s or whatever, right? Until your brain or your body kind of goes, you can do physics, right? So it's a really long career, and there's no point in burning out early. And I also picked this career because I think it has, in my opinion, a lot of freedom and a lot of flexibility. So I think I've just been pretty good at like just not taking stuff too stressfully, right? Like taking stress where I want. What do I mean by that? I mean, I was perhaps not the best student in terms of my math classes in undergraduate. I don't think I attended a single Calc 3 or Calc 2 class. But it worked out fine, right? Like I still got good grades or whatever. And I think it's just like being able to kind of give yourself leeway to make sure you're not burning out so you can maintain effort for a while is how I balanced it. And for me, that was just choosing my priorities. I even if I got grades, and that's just because maybe I like physics and I'm very invested into it, I chose to put stuff like research and rocketry above my classes to a certain extent, right? And it's, again, not like I had it anywhere close to a C or whatever, right? I would be like, okay, am I gonna study 2 hours for this problem set or whatever, or I'm gonna be like, we'll try to clutch up for the exam and we'll spend another hour or so, just in the lab hanging out, or for the record. So I had a pretty cool group of roommates too. They were like, I don't know, go out or something, or throw a frisbee around, or drink and play like Mario Kart or whatever. You know what I mean? Like this kind of thing. And I think it's just choosing the mental stress of being able to defer things for my kind of mental health.
I think for me, I'll just be very brief to move on from the question then. I think what I found is that I always felt I was busy, especially in science classes. I feel like any STEM student finds themselves to be really busy, but what I did is I forced myself to do that extra thing. And I suddenly found myself having the time to do it because you get better at time managing too.
Yeah. I will also say one other thing. I think I was very good. I'm pretty good about just choosing things I actually believe in, right? Like a lot of people, especially when they're trying to resume build, just like, and I notice a lot of med students specifically, so you're right, they just like pick things because they think it'll look good on the resume, but they don't like care about it, right? Versus I think everything I basically invested my time into, I actually cared about. So even my volunteer stuff, so I was like a volunteer for like, the New York election board or whatever, right? And this thing called the Tool Library in Buffalo. Great idea, check it out.
Yeah.
But I like believed in those things. So even when I was doing them, it didn't feel like a drag to me. And I think that's just true of everything, right? Like I believed in physics and doing it. I believed in the rocketry stuff. And in that case, it's not really much of a drag. It's more so just me putting in effort, maybe a bit too much effort, things I actually care about,
Everyone say thank you to Kershs for coming in and giving his piece on theoretical physics. Since we live in the same house, I'm sure he'll be back at some point, but I hope everyone learned something from a lot of this.
Yeah, thanks for the questions. Appreciate it. Some interesting questions. Yeah. All right, cool. I'll leave you to it then.
Sounds good.
I'll let you
dude.
do your AC.
Oh wait, take the chair.
I'm good.
No, take the
I'm good.
take the chair. No, take the chair. Take the chair. No, take the chair. You gotta take the chair. Take the fucking chair! I think he took the chair. We didn't see you guys. Oh, we forgot to kiss! Damn it! Ugh! No! Oh, what? I can't believe I forgot that part! Oh, God! So stupid! I won't forget that next time. I promise. Promise I won't forget that.